All right, welcome everybody. This is going to be our first real topic in dynamics in our series of dynamics lectures, covering rectilinear motion today, or really rectilinear sounds fancy, but it just means motion along a straight line. Hope you're pumped to learn about this. I'm pretty excited, so let's get on with it. So like I said, rectilinear motion is just motion along a straight line. If I were to draw some little 2D axis here with a 0 or an O with the origin, I can designate some kind of position along this 2D axis as S. And if that's my starting position, I might end up with some final position, which I could call S prime. The difference between them, I can show with this little dimension line, we can call delta S. And that delta S is going to be our first real definition. We're going to call that displacement. Pretty exciting, huh? First real definition. And displacement, as I just defined, is our delta S. That's equal to our final position minus our initial position. So let's put a little box around that saying, yeah, it's an important first equation in dynamics. Ooh, buddy. Units of displacement are going to be in units of length, so it could be in meters or millimeters or feet or inches or whatever else you might want to use for units of length. A couple of notes that we should add about displacement is that the sign is important. And the reason the sign is important is because the sign will show the direction of the displacement. So if we had a negative displacement, what that means is I started off and traveled in the negative direction, right? So positive, minus, let's see, so this shows the direction of travel. Also, as another note, this is different than what we use in everyday terminology of distance. So don't mix those two up. It's easy to do, and we'll have some problems that differentiate the difference between distance and displacement. For example, if I were to look at the same 2D line here and I had some initial point S and some final point S1, I know that my delta S is just the difference between those two. However, it doesn't indicate how I got there. Maybe I started off here and went all over here and then turned around and came all the way back. And clearly my distance would be much greater in that case than the displacement. So after we know about displacement, the next term, our second term that we need to define here is velocity. And velocity is really just how quickly this displacement occurs. So for our second equation, lowercase v looks kind of crappy, but let me draw the end. So lowercase v is equal to our change in displacement, ds over dt. And so we can see our units would just be distance over time. So now we're talking about miles per hour, miles over hours, or meters per second, or feet per second, or you get the idea from there. With velocity, we're going to put my little box around it so we have a second official equation here. With our velocity, which is the rate of change of displacement with respect to time, need to add a couple notes there. Once again, just like with displacement, the sign is important because what the sign will tell us is our direction of travel. For instance, if I had a negative velocity, it means I have to be traveling in the negative direction. Positive velocity, I have to be traveling in the positive direction. And just like displacement was different than distance, I know that velocity must be different than speed, because speed is based on distance, not direction, right? So speed would be our distance over time. And since displacement and distance are different, then of course speed has to be different than velocity. After velocity, we can talk about how fast our velocity is changing with respect to time, which would be acceleration. A lot of this should be review. I've already had it in physics, possibly dating way back, and so it's just formal definitions as we build on these. So our acceleration would be our change in our velocity with respect to time. And of course, since we know that velocity can be a change in displacement, then we have our second derivative of displacement with respect to time. And units then would just be meters time over, distance over time squared. So meters per second squared, or feet per second squared, or whatever else you might have. Draw a little box around there. Our equation number 3 in the whole. And there is one fourth equation we can derive because we know that we have from our velocity equation, which says we have a change in our displacement with respect to time. I can rearrange this equation in terms of dt. So doing a little fancy algebra, again, dt is equal to ds over v. My v's are awful today. Don't know what's going on. Too much caffeine, possibly. And we know our acceleration is change in velocity with respect to time, so I can rearrange that equation for dt, and then I get my dt is equal to dv over a. Well, of course, I know that my dt must be equal to dt, so from that I know that my ds, my change in displacement over velocity, must be equal to my change in velocity over acceleration. However, we don't usually write it like that, so rearranging this equation, I get my final equation for the day, which is that acceleration times the change in displacement is equal to velocity times change in velocity. Just rearranging that little equation. And this was probably the hardest to conceive of on how it actually works in real life, but still valuable nonetheless. I do want to put a note about acceleration in general, because if we look at what our signs were important for displacement, our signs were important for velocity because it denotes direction in both cases. However, in this case, a negative sign does not necessarily mean you're traveling in the negative direction. So let's see, our negative acceleration does not indicate direction. And you might be able to see this without a little example, but I could have a scenario where if I had a velocity at one point, and I'll designate my magnitude of velocity with these arrows, I might have some velocity here, and then of course if it gets smaller, I know my acceleration must be pointing in the negative direction to the left. And my direction, of course, was pointing to the right. Or, as an alternative, what we tend to think of is I could have my velocity starting off and increasing as I move to the left, and then I would also have an acceleration that is pointing to the left. So while my direction can be either direction, to the left or the right, my acceleration would be to the left in both those scenarios. So let's look at one little example on how you actually use these equations to solve a problem out of, and this is a problem I took from Hibbler. Looks like it's example 12.1. And let's say for this example, we're going to be given a velocity, I think it's a car's velocity in this case, of 3t squared plus 2t, and our units for this equation are in feet per second. What we are asked to find is the position and acceleration at a particular time, in this case at a time of 3 seconds. So let's start with acceleration. if I look at this acceleration, I know that I have an equation for acceleration relating acceleration and velocity. My acceleration is equal to the change in velocity with respect to time. And I know that my derivative of this velocity, just taking the derivative, I have 3 times 2 is 6, so I end up with 6t plus 2. 2 times 1 is 2. And after I have my equation for acceleration as a function of time, then I just have to say at this 3-second mark, I'm just plugging it in. So my acceleration would equal 6 times 3 plus that 2, or 20 feet per second. Watching my units. Ooh, 26 per second squared. Not watching my units good enough apparently, but get the idea. For the position, I'm gonna have to work backwards, so we have to do a little bit of integration. My velocity, once again, V's are sour today. I don't know. We have our equation that is equal to the change in position with respect to time. So I'm going to rearrange this equation slightly, and I have moved the dt to the other side, and I do that so that I can set up a little integration. Now note that I want this to be, I want to have limits of integration, because otherwise when I integrate I'll have a constant of integration. So if I think about what the limits would be for this ds, for this position, I'm starting at 0 because it doesn't tell me I'm starting anywhere else, and I want to know some final position s. And velocity, I'm starting at a 0 velocity, and I end up with a time at 0, and end up at 3 seconds. If you didn't do that, another way I see people do this is as in basically an indefinite integral. You can integrate, get a constant integration, use a boundary condition, say it at time equals 0. I know my velocity is equal to 0, and you can go that route as well. So with that in mind, I can do the integration, and it isn't too bad. So I'm going to put this to the other side just to make it a little cleaner. 0 to s ds, oh my, is equal to the integral from 0 to 3. So just flipping sides, putting in my equation for v, which is 3t squared plus 2t dt. So this would be s minus 0. So that's basically just, the integral of ds is just s, and then plugging in s and 0 is equal to t cubed plus t squared, and that has limits from 0 to 3. So I can plug that in, and I end up with 27 plus 9, which is a whopping 36 feet. So my location at 3 seconds is 36 feet. So I hope you found this somewhat helpful, and I look forward to working the rest of these dynamic principles with you. So take care.